In this video, I'm going to introduce you to a couple of more terms that are important for hypothesis testing and generally doing inferential statistics. So let's start with IVs and DVs, which are also called independent variables and dependent variables. So the dependent variable is also sometimes called the outcome variable, and that is the thing in the universe that you are trying to understand. It's what you are trying to explain in your data. And then we have the independent variables, which are also sometimes called the explanatory variables. And these are the variables that you are going to use in attempts to explain the dependent variable. So let me give you a few examples. So here's an example of a study. We are looking at the effects of soil moisture on plant growth. So in this case, we have two variables, soil moisture and plant growth. Soil moisture is the independent variable and plant growth is the dependent variable. Now, when you're running an experiment, like in a research lab, then the independent variable is usually the thing that you are manipulating. That's the thing that you are affecting, having a change over. So let's say you have a bunch of different plants and you change their soil moisture. So you have some plants that are dry and some plants that are wet and so on. And then what you're measuring is plant growth. So that makes it a little bit clear. And we can see also the keywords here, effects of, then that's the independent variable. And those effects on is going to indicate the dependent variable. Here we have another example, effects of time spent on Facebook on irritability. So this is probably not a controlled experiment where we are forcing people to spend a certain amount of time on Facebook, but maybe we measure how much time different people spend on Facebook, and then when they close their laptop lids, we can ask them how irritable they are. All right, here's a third example, the relation between money spent on clothes and bar hopping. Now, this sounds like some interesting research, but it's actually a little bit harder to tell which one is the dependent variable and which one is the independent variable. We could imagine thinking that the more people spend on clothes, the more they want to, show off their nice clothes, and so they go out more often. On the other hand, we could also imagine that when people go out to bars more often, then they end up wanting to buy more clothes, so they spend more money on clothes. So sometimes, particularly in these kind of natural experiments where there's no controlled variables by the researcher, that it could actually go either way. So there are cases where the one you call the independent variable and the one you call the dependent variable actually really depends on the kind of question you're asking and the way you're approaching the data and what you hope to answer. Okay, now I'd like to introduce you to the concept of models in statistics and model fitting. So a model is basically our template, our theory about something that happens in the world, and then we have to come up with an equation that represents that theory, and that is the model. And that's ultimately what we use in statistics. We are developing models and fitting them to the data and seeing how well do these models fit the data. So a model usually looks like an equation where you have the dependent variable on one side and all the independent variables on the other side. So let's imagine we're trying to explain how tall someone is. So as an adult, what determines someone's height? That's variable h here. Well, I have a theory, and it says that someone's height as an adult depends on their sex, depends on how tall their parents were, how healthy they ate as a child, and so this is the formula. Now, here we have the variables that we specify. And you'll notice that we also have this extra term in here. It's a funny looking B symbol. It's actually the Greek character beta. So we have beta attached to each one of these individual variables. So these are the variables that I specify as the researcher, as the data analyst. But the thing is, I don't really know how important the parent's height is for an individual's height. So that's why I need this beta parameter here. This beta parameter is going to allow the data to tell me how important this variable is. So if this variable is totally not important, if your parent's height has nothing to do with your height, then this beta, the data will push this beta value to be close to 0. On the other hand, if your parent's height is really, really important, then when I fit the model to the data will push this beta value to be large. So you can see that in these statistical models, there are some components to the model that we as the data scientists can impose. We state this, And there are other features in the model, in particular these betas, these coefficients here, that are fit to the data. So the data are telling us how important is sex and height and nutrition. Okay, and then the last thing we have here is this funny looking E character. This is also a Greek symbol. Statisticians and mathematicians in general really like using Greek characters here. So this is the Greek letter epsilon, and it's called the residual, or sometimes it's called the error. So that's basically whatever is in height that is not explained by this model. Now, it's obvious to you and to anyone that we cannot perfectly explain how tall someone is only with these three variables. Maybe these three variables are important, but that's not going to be the entirety of what determines someone's height. So we have this residual term, and basically everything in height that is not explained by these three variables, by the rest of the model, that all goes into the residual. So you can already start to imagine that if this model isn't good at all, if this is a really terrible model of people's height, let's say we're trying to predict people's height based on, I don't know, the temperature outside, then that's not going to be a very good model. So then the residuals are going to be really, really big. On the other hand, if we have this really rich, detailed model, we have these three variables and something about genetics and maybe the country you were born in and socioeconomic status and the time of year, all sorts of variables that are doing a good job explaining how tall people are, then this residual is going to be small. I hope that makes sense. This is actually a pretty crucial concept in statistical analysis and in model fitting. So in model fitting, we set up this equation, and the way that we evaluate how well this equation, the model, fits the data is by looking at these residuals. So if these residuals are really small, then it means that we have a good model. It's a very accurate model. And if these residuals are huge, then it means that we have a crappy model and we need to rethink what our model looks like. We need to maybe add some more variables or remove some variables that aren't contributing. Now, you can imagine taking this to the extreme and just adding, like 500 different parameters here in this model, adding tons and tons of things until the residuals get smaller and smaller. But there is a principle in statistics which is related to something called Occam's razor that you're probably familiar with from movies and whatever. Occam's razor basically says that the simplest account of the world of some data is the one that we should stick to. And that's a pretty important point that's general to all of statistics. We want the residuals to be small. That means the model is good. But on the other hand, we want the models to be simple and straightforward and not bloated up with more variables than we don't need. Remember, the goal of statistics and the goal of science in general is not to understand absolutely every tiny little detail of how everything works. Instead, the goal is to come up with simplified but straightforward models that do a good job of accounting for data that allow us to understand what's happening in the world around us. So a model should be as simple as it can be and as complicated as it must be. The residuals should be small, but the model should be simple. You can see that there's a difficult trade-off here, and a lot of statistics is really trying to find the right balance between getting the residuals to be small without having the models be too simple that they become meaningless. The last concept that I want to define in this video is an hypothesis. I'm sure you know this word. I'm sure you already have a sense of what an hypothesis is. A hypothesis is a falsifiable claim that requires verification, typically from experimental or observational data, and an hypothesis must allow predictions about future observations. So for example, let's say I have an hypothesis that studying for an exam will help you do better on an exam. That requires verification from data, and it also allows predictions for future observations. Now, let me give you a counterexample. Will many people vote in the upcoming election? That is an interesting question. It's an important question, but is totally not an hypothesis. An hypothesis has to be a falsifiable statement that requires verification, and it has to allow for predictions about future observations. Now, the reason why I mention this is that in statistics, we're usually testing different hypotheses against each other. And so in particular, we always have something called the null hypothesis. And the idea is that the null hypothesis is the boring, uninteresting hypothesis that nothing is happening in the data. And then we have an alternative hypothesis, which you might also think of as the effect hypothesis. And this is what we designed the research to test. So in statistical analyses, you set up your null hypothesis and your alternative hypothesis, and then you do various statistical techniques, which I will explain more in the next section. And those techniques allow you to test the probability that the null hypothesis is true. Now, most of the time, we're more interested in the alternative hypothesis, but we actually test the null hypothesis. This null hypothesis is often written as H with a 0 in the subscript, and it's pronounced H naught. This would be like the British way of saying 0. So H naught, or the null hypothesis. So let me give you a quick example. Our alternative hypothesis, this is the thing that we're actually interested in, is that people will buy more widgets after seeing advertisement X compared to advertisement Y. This is a form of A/B testing that we would use a t-test to evaluate. And then the null hypothesis here is that the advertisement type has no effect on widget purchases.